Now your final exam is going to, be pretty daunting. It's going to include a lot of stuff. I found that the most effective way to prepare for it is to do the problems once, then go back and do them again. So the more times you repeat the process, you'll start to pick up those patterns a little better. You'll start to be able to do them a little more efficiently. So that's one of my hints. So let's start with number 4. It says for the functions, find f of g and g of f and the domains, okay? So let's just do part, for time's sake, let's do part A only, so you can cross out B for me. So if we look at f of g, remember how f of g works. So f of g, we're going to put into the f function the g function. So the g function is the square root of x. And that's going to go right into the f function. So that's going to be 1 over the square root of x squared minus 1, or 1 over x minus 1. So that's what f of g is. Now the question is what is the domain as well? So if we think about a rational function, a fractional function, x minus 1, so you have to first look at two things. You have to look at the final version. So x minus 1 cannot equal 0 because it's a denominator, it can't equal 0. So x cannot equal 1. But then we also have to look at what function we started with. We started with the g function, and the g function is a square root function. So x has to be greater than or equal to 0. But we also know, remember, that from the final version that x is not allowed to equal 1. So the domain is any value greater than or equal to 0 except for 1. Now, you could also, if you think about on the number line, it's a closed circle at 0 and an open circle at 1. So there's kind of two pieces. So if we put it in interval notation, it would go from 0 to 1, and then from 1 to infinity. Okay? Now, they also asked us to go from g to f. So now let's do the g of f. So g of f is the g function with the f function stuck inside. Well, the f function is 1 over x squared minus 1 is going to go into our g function. So it's really going to end up being the square root of 1 over x squared minus 1. And you can't really do anything else. That is your final version. So what does that mean? Well, what screws up the original thing, f of x? Well, positive 1 or negative 1 screws that up. So we know right off the bat that x cannot equal plus or minus 1. Now, why is that? Well, it's a fractional function. What makes the denominator equal to 0? Positive 1 or negative 1. But what else do we need to know? Well, we need to know that this has to be greater than or equal to 0 because it's inside the square root. It's got to be a positive. So do you remember those good old wonderful plus or minus charts? If we put that in factored form, we get x plus 1 and x minus 1. And if we put it on a number line, 1 and negative 1 are our points, but we knew that those screw things up. So let's make those open circles. And I know I didn't leave much room here, but I'm going to put over here x plus 1 and x minus 1. And let's make a little chart. Well, if I plug in something like negative 2, I get a negative here and a negative. Two negatives make a positive. If I plug in something between negative 1 and 1, like 0, I get a positive and a negative, which is a negative. And if I plug in something after 1, like 2, I get a positive and a positive, which is a positive. So we want just the positive version. So we want here and here. So our domain, we already took care of this, and now we needed the positive stuff. And so our domain is anything from negative infinity to negative 1, or from 1 to infinity. You can also say when x is less than or less than negative 1, or when x is greater than 1. So that is your problem number 4. Okay, and just again skip 4b. Now let's go ahead and take a look at number 6. Number 6 says that what is the limit for part A as we approach 1? Now, the thing that should be of concern to you is the fact that we have a border at 1. And so a limit exists if, as the borders approach 1, we are approaching the same height. You have to remember that we do not care what happens at 1. We only care what happens as we approach 1, because a limit is not the same as continuity. If they asked us what could make this continuous, for continuity, the limit has to approach the same thing and the function has to be colored in at that point. But for this one, let's think about as we approach 1 from the left, we are at a height. Now we don't reach the height, there's an open circle there, but we reach a height of 2, or almost, okay? Now, as we come in from the right, we reach a height of 1. Since these do not match, we are approaching different things, the limit does not exist. Okay, so part 6A, the limit doesn't exist. Let's talk about 6B. Now, 6B, it's important, again, that we are looking for a limit as we approach -2, and this is a border. If it wasn't a border, it would be fine. It would be just that value at that point. But let's think about what's happening as we are greater than and equal to -2. Now, the equal to isn't as important as much as the greater than. As we approach it from the right, -2 plus 5 is 3. Now, if we approach it from the left, that would be this point. If we plug in -2, we get 2 times -2 squared would be 2 times 4, 8, plus 2 minus 7, which is 10 minus 7, or also 3. So since we are approaching the same thing from both sides, the limit will be that value. So that is 6A and B. Okay. Okay. Now let's move on to 7. Some more limit sort of stuff. Now, for a piecewise function, remember you have to look at both sides of the number that you're approaching. For a regular, just good old limit, what do? Well, first thing I've always told you to do is plug it in and see what the heck happens. So let's look at 7b. If I plug in -1, I get 0 on the top. If I plug -1 in the bottom, I get 1 plus 4 minus 5, which is also 0. Now, do not jump to the conclusion that it is undefined. The limit as we approach something is the height we're approaching for both sides, not whether it exists at that point. Remember, 0 over 0 is an indication that something good can come of this after all, that we can actually evaluate the limit. So what do? Well, if it's something like 7b, it's a factorable quantity. Now you might not remember, but there is a difference of cubes formula. The sum of cubes is factorable to be a plus b times a squared minus ab plus b squared. So that top is factorable. Every place I see an a, I'm going to put an x. Every place I see a b, I'm going to put a 1. And so that factors to be x plus 1, x squared minus x plus 1. The bottom factors as well. That's going to be x plus 1 and x minus 5. Now, what is causing the issue here is this x plus 1 factor. If we remove it and look at the simplified version, we can take the limit as x approaches negative 1 of x squared minus x plus 1 over x minus 5. So now, try to plug it in again. Well, if I plug negative 1 into the top, I get 1 plus 1 plus 1, or 3. If I plug negative 1 into the bottom, I get negative 6. So the answer is negative 1/2. Good to go. That's your answer. Now, let's look at D. For 7D, we are not approaching 7, but we are approaching 7 from the left. Now, you should always try to plug in 7 and just see what the heck's happening. If I plug in 7 on top, I get 98 over 0. Now, you might recall that a number over 0 did not indicate there was just a hole in the graph, but it indicated that there was a vertical asymptote. So what we know about vertical asymptotes is as we approach that vertical asymptote, we are either flipping up or flipping down to positive or negative infinity. So I know the answer to this is either positive or negative infinity, but I need to discover which one. Well, I'm approaching it from the left, so just find something slightly to the left of 7. So 6.9 is a number that's just to the left. I usually go about a tenth away, and so I'm going to plug in 6.9. So I'm going to get 6.9 squared plus 49 over 6.9 minus 7. Now, you don't need a calculator because I know the answer is either positive infinity or negative infinity. I just got to figure out which. Well, the top is definitely a positive number. The bottom, 6.9 minus 7, is a negative. A positive divided by a negative tells me that I am going to negative infinity, and that's my answer. So it's as simple as that. Okay? Now, 7E is the exact same problem, but we are coming in from the right. So this time, let's plug in 7.1. We already plugged in 7. We know what's happening. And let's ask ourselves the same thing. Well, we get a positive over a positive, so we're going to positive infinity. So the answer to E is positive infinity. But what about F? Limits to infinity will only exist as we approach a number if we are going to the same direction. So let's think about what's happening to this function. Now, I don't know exactly what this function looks like, but at 7, I have a vertical asymptote. From the left side, I'm going to negative infinity, and from the right side, I'm going to positive infinity. So F only exists if I am going to either, from both sides I'm going up, or both sides I'm going down. So this one does not exist. Now let's look at 7, Q, and R. You can even lump P in there. They're all the same, those ones. What I want you to recognize is that this is just the derivative. Yes, it's a limit, but we're not going to use the limit. We're going to use the shortcut we know as a derivative. So what do you need to discover when you're looking at a function like P, Q, and R? Well, here is the f of x sitting right here. Because let's remember what the formula is. It's the limit as h approaches 0 of the function with x plus h plugged in minus the function with x plugged in all over h. So see how each one of these is set up that same way. The function with x plus h plugged in. The function with x plugged in. All over h, we're approaching 0. Everything's the same. That is the derivative of the function f at the value x. So our f of x for q is sine of x. So we know f prime of x is the cosine of x. What's the x we're using? pi over 6. So we just have to do f prime of pi over 6. So the cosine of pi over 6 is our answer. Now here you got to go back to the unit circle, so look over your unit circle before the test. Pi over 6 is 30 degrees. The cosine is square root of 3 over 2. Okay, now let's go to r. Our function is cosine, so f of x is cosine. Our x is just going to stay in x. There's no value sitting right here like there was in P and in Q. So f prime of x is our answer. The answer is negative sine of x. So please make sure to look over your all your derivatives. Okay. Number 8. Number 8 says to define P such that the following functions are continuous at 3. Now remember how continuity works. As we approach the value, the limit has to go to the same height as the value that's plugged in. So this is going to tell us what the limit is. This is going to fill the hole. So what happens is for this one, there's a hole in this function at 3. This is going to plug the hole. Okay? So how do we know that there's a hole in the function at 3? Well, if we plug 3 into this, we get 0 over 0. There's a hole. So how do we plug the hole? So let's look at what we can do. So let's start with f of x. So for 8 f of x, the top is a factorable quantity. Normally, if there's a hole there, you get 0 over 0. Try to manipulate that algebra. This is really x squared plus 1, or I'm sorry, x squared plus 9 times x squared minus 9, okay? So the x squared minus 9s can cancel, okay? So as we approach 3, yes, there's a hole there, but we are really looking at 3 times the quantity of x squared plus 9. X squared is 9, 9 plus 9 is 18, 3 times 18 is what? 3 times 18 is 54. So we're really approaching 54. Now, there's a hole there. So we're really approaching the point 354. Okay. So we want P to fill the hole. So P times our x value of 3 plus 9 has to equal that height of 54, so it fills the hole. And you just solve it. And so we're going to subtract 9 from both sides. 9 for 54 is 45. Divide by 3, get 15. So P was 15. So if 15x plus 9 was sitting right there, it would fill the hole. It would be a perfect match. Okay? Don't worry about 8 g of x. Just do f of x. Okay? Any questions about number 8? Let's move on to number 10. Number 10 says to find asymptotes. Now remember, the vertical asymptotes are for fractional functions where the bottom equals 0. Holes don't count. Those aren't asymptotes. They're holes. And then we also have horizontal asymptotes, which is just like that end behavior. Compare the top and the bottom. I'll remind you as I go. For all of these, first, let's put them in factored form if necessary or if possible. So if we look at 11a, it's totally ready to go. Let's look at 11b. Let's get that in factored form. So that's going to be x minus 2 and x minus 1. And the bottom in factored form is x minus 2 and x plus 2. Okay. So there's technically a hole at that one. C is fine, but we'll discuss that in a little bit. D, let's get that in factored form. That's going to be x plus 3 and x minus 3. The bottom's going to be x minus 2 and x minus 3. And that x minus 3 is a hole again. Okay, so let's start with 10a. Now that they're all ready to go, again, we'll discuss C in a minute. let's look at all our denominators. Let's do our vertical asymptote. So there's a vertical asymptote where x minus 1 equals 0. We're at 1. For number 10a, there's a vertical asymptote at x equals 1. 10b, we're only concerned about the factor that's left. So the vertical asymptote is x plus 2 equals 0, or negative 2. For 10c, there's a vertical asymptote at x equals 0. In 10d, there's a vertical asymptote at the factor that's left, x minus 2 equals 0, so x equals 2. So the vertical asymptotes, remember, after you've discovered the holes, then account for all the vertical asymptotes. Now let's take a look at horizontal asymptotes. So let's do A, B, and D, and then we'll discuss C a little bit. For A, the horizontal asymptote, we are going to compare the power on top with the power on the bottom. They match, so we can just use the coefficients. So it's just going to be y equals 1 over 1, or 1. B, same thing. We're just using the simplified version after we remove the whole. It's going to be y equals 1 over 1, or 1. Same exact thing for D. The horizontal asymptote is going to be y equals 1 over 1, or 1. Now, C is a little different. The left end does one thing and the right end does another, and here's why. So if you isolate the highest power on top, it is the square root of x squared. So we're technically looking at the square root of x squared over x. Okay. Now, if we go to the right side, we're plugging in positive numbers. The positive numbers are getting very, very big. And so if we plug in positive 1,000,000, square it, then square root it, we get 1,000,000 over 1,000,000. It's 1. Okay. So the left end, or I'm sorry, the right end is y equals 1. Okay. But let's talk about the left end a little bit. If you plug in a negative 1,000,000 and you square it, it becomes a positive, square root it becomes 1,000,000. But it's still over a negative 1,000,000. And so what happens is that square kind of screws things up. So the left end is going to y equals negative 1. So kind of an interesting thing happens because of that squaring and then square root process. Okay. So there is 10. We're skipping 11 and we're jumping to 12. Now 12, 13, and 14, we're going to try to get those done right now. Those are all about rules of derivatives. And so you do have to remember all your rules of derivatives. And I just want to practice doing some of those. So let's start with number 12. So the first thing I would say about number 12 is let's do a little rewrite. Remember those rewrites to make your derivative process nicer. Now, this is a perfect example of a chain rule. We have stuff stuck inside of that 1/2 power, so you are going to have to use a chain rule. So the derivative is going to be 7 times the half drops down, so that's 7 halves. The stuff stays where it is. The power goes down by 1. So the power was a half, it goes down by 1, so it's going to be negative 1/2. And then you have to multiply by the derivative of the stuff inside. So the stuff stuck inside is this x to the 4th minus 15. Its derivative is 4x cubed. Now that's just the derivative. We do want to find the derivative when x is equal to 2. So let's now plug in 2. So we get, did I do something weird? Maybe.
Is it supposed to be 1/2 or negative 1/2 on the first section?
Oh, thank you so much. Yes. Yes. So that was a negative 1/2. So this would be a negative, wait. So this would be a negative down in front. Thank you so much for catching my weirdness. And this would be a negative 3/2. Better now? So Kira noticed that this, when flipped up, should be a negative power to begin with. So now this is correct. And then we do the derivative on that. So the negative drops down in front. This goes down by 1, so negative 1/2 minus 1 is negative 3/2. Everything's good now, I think. Okay, thank you. Okay, so now let's plug in 2. So we get negative 7/2. 2 to the 4th is 16. 16 minus 15 is 1. 1 to any power is just 1. 4 times 2 cubed is 8 times 4. 8 times 4 is 32. And then times 7/2, 2 goes into 32 16 times, and 16 times 7 is negative 112. Okay, so there's 12. Let's do 13. Let's do a little rewrite. I think the rewrite should be 2x plus 17 to the 2/3. Remember, the power is your denominator or numerator, and your index is your denominator. So the 2 goes on top, 3 goes on the bottom. So when we do the derivative of 13, the power drops down in front. Leave the stuff alone. Drop the power down by 1. 2/3 minus 1 is negative 1/3. Don't forget to multiply by the derivative of the inside. Now we have to plug in 5. So that's 10 plus 17, which is 27. Now, a 1/3 power means a cube root. So the cube root of 27 is 3. What the negative does is it flips it and makes it 1/3. So this really becomes 2/3 times 1/3 times 2, which is 4/9. So the answer to 13 is 4/9. And then let's do 14 before we say goodbye. Okay, so for 14, I would do a rewrite. Pull the 8/3 in front of the x so you can really see that that's just a constant. For the 3/8, I'm going to pull that out in front too. But since the x was down in the denominator, I need to rewrite it as a negative 1 power. So that's our function ready to take the derivative. Now when we do that, the derivative is pretty straightforward now. So the derivative is going to be 8/3. And then the negative drops down in front, multiplies by the negative that's already there, making it a positive 3/8. Power goes down by 1. Now we have to stick 1 in for all the x's. The only x left is the one in the back, so it just becomes 8/3 plus 3/8. Make those 24ths. So that's going to be 64/24 plus 9/24, which is 73/24. Okay? So we will continue the next time we're together where we left off. So, I would maybe try these problems again on your own. That's a really great way to prepare. And there you go.